Okay, hi. So this is our third video, and the goal is to prove Theorem 51 of the textbook. So let's see what the result is. Suppose f and f prime are two fields, and you have an isomorphism sigma from f to f prime. So now we're assuming that sigma is an isomorphism. Let f be a polynomial with coefficients in f. We're not assuming that this polynomial is irreducible necessarily. Let E be a splitting field of f over the field f. Also, okay, so we have this polynomial sigma star f obtained by applying sigma to the coefficients of f. It's a polynomial with coefficients in f prime. And let E prime be a splitting field of that polynomial over f prime. So the picture looks like this. We have sigma and isomorphism from f to f prime. We've got a polynomial f with coefficients in f, and E is the splitting field of that. The image of f under sigma star. Okay, so that's a polynomial with coefficients in f prime, and we're assuming that E prime is the splitting field of that polynomial. And now, what's the first assertion? The first assertion is that there exists an isomorphism, sigma hat, from E to E prime, which extends sigma. So again, if the two fields are isomorphic to each other, by an isomorphism sigma, the two splitting fields are also going to be isomorphic to each other. There's going to be an isomorphism which extends your original isomorphism between your f and f prime. That's the first assertion. The second and third assertions are about the number of sigma hats, number of sigma hats that we can have. The second assertion, part B, is that the number of isomorphism sigma hat from E to E prime, which extends sigma, is at most the degree of E over f. And the final assertion is that if we further assume that every irreducible factor of f is separable, which is to say that it has no repeated roots, if every irreducible factor of f is separable, then the number of isomorphisms sigma hat from E to E prime extending sigma is exactly equal to the degree of E over f. So now we're going to prove this theorem. Unfortunately, I have to cover the statement. But the diagram is here. So we've got an isomorphism sigma from f to f prime. And f is a polynomial with coefficients in f. E is a splitting field of this polynomial over f. We're not assuming that the polynomial is irreducible again. And now E prime is a splitting field of sigma star f over f prime. And the goal is to show that there exists some isomorphism. So the goal in the first part is to show that there's some isomorphism sigma hat from E to E prime that extends sigma. Okay? So now let's prove this statement. So prove in part A, which is about existence of a sigma hat, we're going to argue by induction on the degree of E over f. Let's call that degree n. The degree of E over f. Okay, the base case is n being equal to 1, and that's clear. The assertion there is clear, right? Because see, if n is 1, okay, so what does that mean? That means that E over f has degree 1, which is to say that E is just equal to f. Which is to say that, well, our polynomial f Well, it's a splitting field over F is F itself. So our polynomial already splits over F. F already splits over F. And well, that implies that sigma star F already splits over F prime. Just apply sigma star to the factorization of F. So sigma star F splits over F prime, which is to say that E prime is equal to F prime, and now you just take sigma hat to be sigma. And that's it. So that's the base case. Now we're going to assume the assertion up to degree less than n. So now assume the result for a splitting field of degree less than n over F. Okay. Let me make sure that we don't lose the camera. Sorry. Okay, so assume the result for extensions of degree less than n, and now, okay, so the first, and well, now suppose E is so E over F is now degree n, right? Now, okay, there's two cases here. The first case, so if every irreducible factor of F has degree 1, then, okay, if every irreducible factor of F has degree 1, that means that every irreducible factor of F over F has degree 1. Well, that means that F already splits over F, and it's exactly the same as there. Then F E will be F, E prime is just F prime, and take sigma hat to be sigma. So we're done. Let's assume that our polynomial F has some irreducible factor of degree bigger than 1. Okay, now suppose F is equal to, let's say, G times H. G and H here are in F bracket X. G irreducible, right here, it should be visible, right? So G irreducible of degree, let's call the degree of G D, and let's say bigger than 1. So let me just make sure that everything is visible. Good. So now we assume that our polynomial F has an irreducible factor of degree D larger than 1, greater than 1. Now here's what we're going to do. Okay. Alpha, so see, the F splits in E, so any factor of it also splits in E. G has a particular root in E. Let's call alpha one of its roots. So let alpha in E be a root of a G. And similar story happens on the other side. So sigma star, okay, so sigma star is a ring homomorphism. Sigma star factors as sigma star G times sigma star H. Sigma star G is irreducible because that, well, sigma is an isomorphism, so is sigma star. Sigma star G is irreducible, degree bigger than 1, and well, it splits in E prime. So let alpha prime be a root of that. Alpha prime in E prime is root of sigma star G. camera.